We'll get going. Welcome, everybody. My name is Jared Monson. I'm a technical animator on the advanced character team, focused mostly on MetaHumans and character technology. I'm very excited to be here to be able to talk about some of the MetaHuman features found in the Talisman project, which was shown at the GDC demo this past GDC. And I hope to be able to give you some insights and some of our approaches and things that we did to help make MetaHumans more efficient and smaller in size. We'll go pretty heavily into that and a lot of more technical details. This talk will be based on the talk that I gave at GDC, but I'll be taking a different approach. Like I said, we'll be looking a lot more into the technical side of things and kind of the processes that we did to optimize the MetaHumans, as well as more emphasis and focus on the UE side, because that's where we spent most of the time, and how we actually got the MetaHumans optimized enough to be in UEFN. We'll also talk about some of the cloth features that were used in Talisman, and also the new panel-based clothing system. Kind of go into that and some of the details there, and kind of help hopefully demystify and show you some of the cool stuff there. If you haven't seen the GDC talk, you can find it on Epic's YouTube channel. It's called Achieving Realistic Visual Styles in UEFN. Again, that talk focuses more on the UEFN side of things and just kind of more of a general overview of what we did to get those MetaHumans in UEFN. And also the new USD clothing pipeline as well. You can check that out, again, on Epic's website. But to help give some more context for this talk and help any of those of you who haven't seen the Talisman demo, here is a quick teaser of that project.
I'm glad you're here. The crew's been waiting for you, and we're ready to help you build what's next. Come on, let's go.
Okay, so yeah, that Talisman demo was all done in UEFN, and if you haven't had a chance to see that demo, you can also see that on Epic's YouTube channel. That's in the State of Unreal address. You can get some more details there. That sample project actually will be releasing pretty quick as well, and you can get the environment, the clothing, and pretty much that whole project to check out as well. There's a lot of good information there for you to check out some more. All right, so let's further break down what we'll be covering and how we'll get there. First, we'll go over a brief recap of what MetaHumans are and go over some of the basic knowledge as a refresher. Next, using UEFN and the Talisman project as the backdrop, we'll look at what we were able to achieve with optimized MetaHumans and set the context for what we did and why. After that, we'll look at the differences between an Unreal and UEFN MetaHuman, and then get into some of the nitty-gritty details of what actually changes and what those differences are. We'll then get to talk about some of the new clothing features and simulation tools that are available in Unreal 5.4, and we'll take a look at the cloth pipeline and how we use it for Talisman, and then I'll also cover some of the lessons learned from using cloth in that production. And hopefully that can give you some tips and tricks for you and help you out. And then to wrap it up, I'll show just a brief rundown of how to add custom clothing to the MetaHuman blueprint and be able to add your own custom clothing. So without further hesitation, let's get to it. So let's first start off with a brief recap of the MetaHuman ecosystem and the tools available for you to use on your projects. MetaHuman Creator is a cloud-based application that allows you to create high-fidelity digital humans. Through an easy-to-use interface, you can quickly and intuitively create photorealistic digital humans, fully rigged and ready to use. Through the power of MetaHuman Creator, you can make MetaHumans in minutes, starting from one of the preset characters or based off of your own custom mesh to be used and then in the Creator app. The MetaHuman plugin for Unreal includes Mesh to MetaHuman, which is an exciting feature that enables you to turn a custom mesh created by scanning, sculpting, or traditional modeling methods into a fully rigged MetaHuman. After converting your mesh, you can further refine your character in the MetaHuman Creator. Also available in the MetaHuman plugin is MetaHuman Animator. This feature set enables you to capture an actor's performance using an iPhone or stereo HMC, and then translate that capture into a high-fidelity facial animation to be used on MetaHuman characters. Every subtle expression, look, and emotions accurately captured and replicated on your digital human. It's really simple and straightforward to use, and the results are great, and really anybody can use it. The animation produces processed locally using GPU hardware, and the final animation is available in minutes. MetaHuman DNA is an integral part of MetaHuman functionality, and these files are created in MetaHuman Creator and downloaded in Quixel Bridge in UE5. DNA calibration is a set of libraries and tools used to inspect and modify MetaHuman DNA, all bundled into a single package. These tools are provided via a GitHub repository for you to download and to use to customize your own MetaHumans. All right, so with that, Talisman was our internal project to test MetaHumans and to kind of push the boundaries of environments in UEFN. And this set the stage for the work we needed to accomplish to get MetaHuman assets small enough and performant enough to hit the specs that UEFN requires. To give us a better understanding of the challenges we were facing, let's take a look at some of the requirements that UEFN enforces. So UEFN enforces certain restrictions for a better user and player experience, and we were made no exception to that rule. There's currently a 2 gig total project upload size and a total download size of 400 megs for a UEFN island. The interesting thing is the average MetaHuman cook size comes in at about 800 megs. So that's 400 megs over the limit of total limit of one island. So basically, one MetaHuman is the equivalent of 2 total UEFN islands. So since we were going to be working within those parameters, we knew we were going to have to get creative and come up with ways to pack in as much as we could, but only what was absolutely necessary. We also knew we had to retain the high visual fidelity, MetaHuman fidelity that we've all come to expect, and we ended up taking a hard look at every aspect of what made a MetaHuman and determined its impact on the overall outcome. And so after a lot of hard work and effort, I'm really excited to show you the results of what we were able to accomplish. So here is a one-to-one comparison of a UE and UEFN MetaHuman, UE and UEFN. The average UE MetaHuman cook size, like I said, is about 800 megs, while the average UEFN version is just 60 megs. That's basically a 93% reduction in overall size. You can see here that even with a significant size reduction, we were still able to maintain a high level of realism and fidelity, and this achievement is what allows you to nearly have the same great visual quality in an optimized MetaHuman as you do in a full-scale MetaHuman. As you really start to look closer, at the images, you might be able to start to pick out a few of the visual differences. The peach fuzz has been removed, and some of the finer details like wrinkles and freckles aren't quite as sharp, but even after pointing those out, differences are pretty hard to notice. And so a pretty huge win for us. Here we can see a wider spectrum of characters with their upload size in blue and their cook size in purple for each of the 3 quality options that you can download in MetaHuman. In the top right corner, we can see an average size of these characters. The average high quality version for all these characters is an upload size of 128 megs and cook size of 55 megs. One of the biggest factors to the overall size and performance of a MetaHuman comes down to the type of groom that you've chosen for your character. But despite whatever groom you choose, your actual cook size won't vary by much, thanks to those optimizations done across all the characters. And this means that you virtually can choose any character you want and pretty much have similar performance across the board. Here we can see the results of the high-quality level UEFN MetaHumans across different platforms. With UEFN Islands being able to be played on across all major consoles, we wanted to make sure that MetaHumans was looking their best, whatever console they're seen on. From high-end to handheld devices, you can expect good-looking results across the board. So going through this process of getting MetaHumans into UEFN led to many improvements and optimizations, and I'm excited to share the lessons learned along the way. So depending on your project needs, you too can customize your MetaHumans using these techniques and to hit the quality and performance bar that you're looking for. To help us get a better overall understanding of the differences of a UEFN version and an Unreal full-scale MetaHuman, let's take a look at how they're processed and what happens when you download your character. When you download a MetaHuman from MetaHuman Creator, you get the complete unprocessed assets in their highest quality state, and then you take that MetaHuman, do your own processing for whatever your needs are, and with an Unreal MetaHuman, you have the options to cook what and however you want, giving you complete control over the entire end-to-end process. For the UEFN versions, we have chosen to pre-process assets and made decisions for you that make the most sense for that platform. You have fewer decisions on how that character is actually processed, but the benefit, it's already in a great state for cooking into UEFN scenarios. One thing to note, though, is that we're currently in the process of making these optimized versions available for you to download and use in Unreal. Currently, they're just in the UEFN state, but these optimized versions will be basically have the exact same setup as UEFN, but without the UEFN-centric features. And the one catch, though, is that we don't know exactly when that will be, but hopefully within the next short little while. So these will be options for you to use and download in UE as well. But again, using the same kind of pre-processing approach, you can take your regular MetaHuman, do some tweaking to kind of fit your needs, and then use that version for whatever your scenario is. So let's take a more in-depth look at the pre-processing we did to create these optimized versions. The most important part that we wanted to make sure is that the underlying optimized MetaHuman continued to work with all the MetaHuman tools. And in order to maintain compatibility with the MetaHuman ecosystem, we needed to make sure what we reduced wouldn't affect your ability to use any of those tools. So with that in mind, we knew we wanted to use existing meshes without changing any geometry, as well as maintain the current rigs and skeletal hierarchy. These two areas we knew we weren't going to change because it would have an adverse effect on your ability to use any of the tools. So using this approach also meant using this approach as far as using the existing meshes meant we didn't need to create a new set of assets to maintain. So all the UEFN or optimized MetaHumans derive all of their assets from their Unreal original counterparts. They're just tweaked to meet the needs of UEFN specs. So in order to reach the performance benchmark that we needed for the UEFN islands, we determined 4 areas that we thought we could get the biggest impact on improving overall size and performance while also maintaining fidelity. And these 4 areas we felt we could improve on were reducing the amount of mesh LODs, general animation performance improvements, groom reductions, as well as texture and material optimizations. And so we'll dive into each of those sections. The easiest one we felt was simply just to reduce the amount of mesh LODs that we used for the characters themselves. LODs mean level of details. When you download a UEFN MetaHuman, you have the option to select from 3 quality levels. High quality is intended for MetaHumans that will be seen up close. It takes up more space in your project than a medium or low quality, but that should perform equally well when using the LODs at a distance. So medium and low quality settings are simply stripped down sets of the high quality version and can be used when close-ups aren't needed or for greater performance in those scenarios. The mesh LODs that we chose to use are derived again from the original MetaHuman asset, but let's take a look at an image that might help visualize this a little bit better. So if we compare how the UEFN MetaHuman level of details or LODs compare to the Unreal MetaHumans, as mentioned before, the UEFN LODs are derived from the original ones, but they're not a one-to-one mapping. So we can see, based on the left-hand side, that a LOD 0 high-quality UEFN character or optimized character is using LOD 1 of a UE MetaHuman face and LOD 0 of a UE MetaHuman body, and so on down the line. So the optimized versions have a subset of the original LOD. We chose these LODs because they have the highest fidelity and performance and quality with the lowest amount of footprint size. And in order to maintain the fidelity of the next scene, we chose the corresponding head and body LODs that it lined up to assure those edges properly synced through the LOD sync component. So speaking of LOD sync component, I'd like to talk a little bit more about the LOD sync component. The MetaHuman blueprint brings together all the different components that make up MetaHuman's visual representation, and that's what you can see here in the image is all the different components of the MetaHuman. So the LOD sync component manages and synchronizes LODs across different MetaHuman components so that they switch at the same time rather than individually like normal LODs do. This maintains the visual quality and consistency of all the components even when they don't share the same number of LODs. For example, the face, as well as all of the grooms, use 8 individual LODs, while the rest of the body and body components and legs and feet, they only use 4 LODs. So for every 2 LOD changes that happen on the face and groom components, only 1 LOD change happens for the rest, and the LOD sync component is what controls this behavior. So when adding your own custom assets in the blueprint, you'll need to update the LOD sync component with your asset and configure how you want its LOD sync how you want its LODs to sync with the rest of the MetaHuman. And there are 3 attributes I want to call out. The first being force LOD attribute, and this attribute will force your whole character to use a specific LOD. The -1 value is the default value and will let the system do the driving. However, if there is a specific LOD you would like to see or debug, then you can specify a value and see the results in the blueprint viewport as well as the editor. We use this quite a lot to visualize specific LODs, what they look like, and then obviously to make sure that those LODs are syncing as expected. So that's a really helpful, it's kind of a debug tool, so to speak, where you can actually just force a LOD. Sometimes we use that as well in for like cinematics and stuff, so that the character always stays at LOD 0 at the highest quality and it doesn't LOD out. The next attribute is the components to sync. This section determines which components are included and which components are driving the others. You can see that the body and face components are set to drive the other components, and this means that whatever the LOD the body and face are using, the rest will use that corresponding LOD, even if their individual settings are different. And here you would add any custom components and set its sync behavior. So for example, if you added a chaos cloth component, you had some dynamic cloth, you would add that to your blueprint, and then you would add it here and likely set it to passive to sync along with the body so that the body and those LODs always stayed in sync. The driving, let's see. Yes, the driving skeletal mesh components get its screen setting size from the skeletal mesh asset itself. So like the actual screen size settings. And in this image is from the body scale mesh. The screen size setting for LOD 0 is set to 1.2. And this setting will determine when the LODs change and drive the rest of the components in the LOD sync. In this image, the screen size attribute is grayed out, and that's because the MetaHumans, we use a data asset to share LOD settings across all the MetaHuman body types. You can open the MetaHuman LOD data settings there and change values if you need to, or you could also clear out that setting and it will only affect that individual asset. The third attribute to be aware of is the custom LOD mapping, and this is where you control how the LODs map to each other. And since the face has 8 total LODs and the body only has 4, the body component is being mapped with a 2-to-1 ratio, and the same with the other components. So if I added that cloth asset and a mesh had 4 LODs, I would add that component to this section and use the same 2-to-1 mapping. One last thing to note too is that the LOD sync component is not a MetaHuman-centric component at all. You can use this and add it to your own custom characters and have all the same features and benefits. And I feel like it's probably a very underutilized component to know. So hopefully that gives you a little bit more information about that. The next area of improvement we wanted to investigate was the animation performance side of things. We knew we didn't want to make any changes to the skeletons, but felt we could find optimizations in the animation system. And so by breaking down the animation compute distribution, we were able to get a better idea of what areas were taking up the most compute time and where we could start looking to improve. We noticed that the post-process anim blueprint was using a lot of compute time and realized we didn't have many options to tune that area either. We then created the UEFN MetaHuman component that allows you to scale your MetaHuman anim blueprint from a fully enabled character down to only running the skeletal mesh, which essentially all the post-process, essentially you can turn on and off anything that's running in the post-process blueprint, like the pose correctives and stuff. Depending on your character, you can expect about a 20 times faster difference between a fully enabled and fully optimized, meaning just running the skeletal mesh. These optimized UE MetaHumans will also have the component as well when they release. So the UE version will have this MetaHuman component, which you can also scale those settings as well. So when profiling the Anim blueprint, we discovered that pose drivers, rig logic, control rig, rigid bodies, and IK fix-up can be expensive depending on their complexity, and we utilize all of those features in both the head and body post-process animation blueprint. So in order to help combat that performance cost of those nodes in Unreal, we added a LOD threshold attribute to each of those heavy compute nodes. And by setting the LOD value there, the graph will stop evaluating that specific node after that LOD number is reached. So in this case, where you see LOD threshold 0, after LOD 0, it will stop evaluating that specific node. To further optimize animation, there's now a post-process threshold, NBP threshold on the skeletal asset. And this threshold will bypass the Anim blueprint altogether, not processing the graph at all, and further getting you more performance. Obviously, the main trade-off here is that your quality of deformations, particularly in the post-process correctives, they won't evaluate or anything else that you have in the post-process blueprint, but that will, again, from the previous slide, that will give you about a 20% savings, or 20 times. We did find that the net correctives and the face post-process animation blueprint can provide a big performance win without losing a lot of deformation quality. These correctives are used to help fix the shape of the neck, especially in extreme poses. And you can set the LOD threshold, again here, to a higher LOD or simply disable them. The trade-off here is the neck shape won't be as nice as it could be in certain poses, again, particularly in extreme poses. But you can find all of those optimization settings here in the Anim Preview Editor window. So those, again, are ways to get some more performance back. I did want to mention some animation performance and profiling tools available for you to use. The editor and control rig all have tools that can help you with profiling. The stat console commands are a great way to get quick metrics of your character or scene, and these commands can be accessed in the editor window under the stat menu or through the console command as well. The command stat unit is a great command to get an overall sense of what times are like on the different threads. The stat unit graph will show you the frame time stats over time, and stat anim will show the current breakdown of the anim game thread. More information about those can be found on the Unreal documentation website as well, but there's a lot of, these commands that I've listed are some of that I use the most often, and to make them more accessible, us tech animators have created an editor utility widget and just made buttons to easily turn those on and off, and I highly recommend utilizing editor utility widgets. I think they're very underutilized as well, just to make it easier to get to some of these console commands. There's a lot of commands we use, like we have essentially a character debugger UI that we've just collected all the tools that we like and we just put it in there. A really great feature of the control rig is the ability to use the VM profiler, and it's basically a heat map that shows you which nodes are most expensive, and this is a great visual tool to find out quickly areas of the graph that could possibly be reworked. We use this feature to easily discover a function that was very expensive. We ended up removing that function completely from the graph and chose another way to solve the problem, and it gave us about a 24% increase just in that specific control rig. And you multiply that across all the MetaHumans, and that's a pretty big win. So just from visual debugging. More information about the VM profiler can also be found on the Unreal website, but definitely recommend using that. Animation Insights is a plugin for Unreal Engine that you can use to profile and watch your project's gameplay and animation systems performance in real time using visual trace data. And by recording trace information during editor simulation, you can see your project's performance bottlenecks and get deeper insights into possible areas of optimization. The Animation Insights plugin contains a graph to observe gameplay and animation system performance. Animation states and live behavior updates, such as variable and blend values over time, are also recorded. So by tracing your project's data, Animation Insights will track changes in data values and plot that information in the color-coded tracks, which you can further debug and optimize your project. So if you want to get a little more technical information, that's a good way to go there. Other area to consider for animation performance is the bone influences per vertice, or IPV. In order to achieve a high level of fidelity in the MetaHumans, they use a face influence of 12 IPV. The rest of the MetaHuman skeletal meshes use an influence max of 8. You can turn down the IPV on the face, but at the cost of some fidelity, as you can see here. And you can change that setting in the skeletal mesh asset. You can see here the differences between 8 and 12 IPV in an extreme pose where you'll notice it the most. When changing to a lower IPV, you'll start getting some crunchiness kind of around the curves of the face, so you'll probably not want to do this if you're doing a close-up or looking for really high quality facial animation. But just another area, maybe you're not ever going to get that close. And so this is another area that you can bump back and get some performance. All right, now let's take a look at grooms. So grooms can be very expensive. So we felt there could be a lot of potential to be savings to be found here. And once grooms were actually enabled and working in UEFN, our challenge was to make them optimal enough to hit performance benchmark required by UEFN. And solving these challenges ended up working in our favor because we found benefits and improvements for both Unreal and UEFN, kind of just general improvements across the board, and you can benefit from all of these changes and optimizations as well in 5.4. So while this is not an extensive list, here are some of the groove improvements that have been made, and I'll just cover a few of them. Strand auto-lotting adapts the number of curves based on the screen coverage of a given groom. We can trim more of what gets simmed, interpolated, deformed, and actually rendered. And this also allows for smoother transitions between LODs, which reduces the amount of popping that you see between them. We've also optimized these curves for faster shadowing and ray tracing. Optimizations were done to textures that require the use of less textures, use a reduced texture resolution, and shrink the overall texture size. The new compact layout is packed into 2 textures for hair cards. The attribute map that contains coverage, seed, and depth in RGB is kept at a larger resolution for card opacity. It varies between 2K and 512 depending on the complexity. And the tangent map is packed together with the strand U in the alpha channel, and this map is between 512 and 256. Cook optimizations were also done, which reduced the cook groom asset by about 50%, which is really awesome. And more optimizations and improvements have been made, and there's also a really cool new hair card generator that also came out with 5.4. For groom performance and optimizations, here are a few tips that we find helpful. We'll first start with the grooming stage, and we'll typically reduce CV count and density to optimize as much as possible. In terms of density, we compensate for the slightly lower density by increasing the hair width. And we try to find a good compromise in terms of balancing look and efficiency. Longer grooms that are wavy or curly will obviously need or have more points to begin with. We optimize these assets as much as possible in Houdini by keeping the curve count roughly under 100,000 and culling points in areas that are less visible. Now, when an asset is imported in Unreal, a warning is given if limits aren't respected. So groups are limited to 4 million curves each, and each of those curves is limited to 255 points. And for the guide count, we're now aiming to keep the number under about 2,000. To help with optimizing grooms, improved debug tools are available for use in the groom asset window. For debugging and profiling, we have options for visualizing groups, LOD color, attributes, guides, CVs, voxels, and memory. And there's a lot of console commands as well, such as voxel size and lighting. So for example, the r.hairstrands.dump outlines the memory footprint of both the groom and binding component, and this is a great way to get a good overall idea of how expensive your groom is. And then further tools, and there's quite a bit of information online in the Unreal website for grooms. One other trick when working with MetaHumans and groom is the use only cards option on the groom component. So hair strands are expensive, it's just the reality, and you don't always want to use a lower LOD setting. So currently the strands will LOD out, but by turning this on, you can use the same LOD but have the hair strands swapped out for the hair cards, which will further increase performance. There's many aspects to consider when working with grooms, but hopefully this can give you a few ideas for optimizing and point you in a good direction. One of the areas that we thought we could make some of the biggest improvements was on the material and texture side of things through baking textures, shared base material efficiency, simplifying operations, and less instructions. We were able to reduce the material and texture size by quite a lot. Our look dev artists put a lot of time and effort into making sure that the MetaHumans retained as much high visual fidelity that their Unreal counterparts have, but in a significantly smaller size. So let's take a look at some more of the details here. So textures account for 90% of a MetaHuman cook. 59% are just textures that are used on the face alone. So the main reason for this is MetaHumans are built for really high quality and fidelity. MetaHuman ship with 6 8K normal maps used on face materials, from which three are the normal maps used for the dynamic wrinkles. And the cook size of just those normal maps alone average about 30 megs. So with textures being such a large part of the total asset size, an easy win to reduce the size is simple enable lossy compression. Even the lowest level of lossy compression can massively reduce the overall footprint of textures in your project. So let's take a look at the cooked asset size for MetaHuman before and after enabling Oodle lossy compression. So here's an average size cooked MetaHuman and its breakdown of assets. We can see the face textures account for over half of the total cook size at 59%. Body and clothing textures take up a big chunk as well, as 31%, and all of those add up to about 782 megs. So by just enabling the lowest Oodle compression, the new cook size went down from 782 to 404. That's about a 48% reduction in the overall cook size of MetaHuman, and the face textures dropped 269 megs, the body and clothing 107 megs, and the groom down to 2.2. That's not a bad win for a single asset change in the texture assets, and this is just one single MetaHuman, so that's a really great option to use, and to be completely honest, even in the highest Oodle compression, we noticed very, very little visual fidelity loss in that. So that's definitely a big win there. All right, for UEFN, we knew we wanted to bake textures, combine maps, and simplify materials. And when deciding how to bake the textures, we chose to use a combination of Python and blueprints on Unreal rather than just C++. Working in blueprints allowed artists to iterate quickly without the need to change engine code each time they wanted to make an update. And this also reduced the overall demand for time and support from engineers. Choosing what to bake essentially came down to just striking a balance between visual quality and memory footprint. Having look dev, like AB look dev environments, also was very crucial for us and our artists to figure out what we could reduce and making those correct decisions. All right, let's take a closer look at the optimized materials we shipped for UEFN. As mentioned before, a total UEFN island cannot be larger than 400 megs, and all published UEFN projects are expected to run on any console from high-end PCs to handheld devices. So to help cover the large range of consoles and be performant, 3 base materials were used. 1 material for the eyes, 1 for the skin, and 1 for the clothing. And for our purposes, we'll just kind of focus on the skin material, and it probably had the most extensive testing across all the different platforms and has the most interesting of uses of LOD and quality scalings. So for face materials, we ended up with 3 material LOD instances. Each material has its own resolution settings and is only used for the corresponding LOD level. And this is for 2 reasons. First, features like animated maps are expensive, and so we reserve it only for the highest LOD. Features like subsurface profiling get disabled at the lower LODs to gain performance. And then secondly, as we drop to lower LODs, the vert count reduces, therefore limiting the geometry available for shading. And in order to maintain acceptable visual fidelity, we use a low resolution normal map based from the high resolution geometry to fake the geometric details on the lower LODs. At lower LODs, we assume the user will be using the MetaHumans at a distance or on platforms where they cannot afford subsurface scattering, shadowing, or ray tracing. And so then we add fake subsurface scattering and ambient occlusion as cheap material functions to make sure the MetaHumans feel plausible at distances using non-PBR approximations. In the lower LODs, we also bake grooms to save performance where it makes sense, like eyebrows and some mustaches. And for comparison, the original UE skin material is about 577 megs, and the new UEFN version is about 13. So the highest LOD material we expect to be used for hero characters and cutscenes, so it uses the following features. It has a bent normal, material ambient occlusion, animated maps, 3 wrinkle maps for normals, and 3 blood flow maps for base color. It also has a subsurface profile. The medium LOD material we expect to be used for NPCs and hero LODs for more mid-range hardware. So this material simply just removes the animated maps. And then the lowest LOD material disables as much as we can get away with and enables some fake subsurface scattering and fake AO to help make the MetaHumans feel more integrated into the environment. Most of the magic for creating the materials happens in a blueprint that our team created, and this is a blueprint. This blueprint is an editor utility, and it can be executed directly on assets in the editor. So to give you an idea of how we set this up, let's just go over the basic idea of how this material function works. First, the function gets the skeletal mesh, gets the associated body material, and then sets a baking material. Next, we set scalar parameters, values on the baking material to enable or disable whichever parameter we want baked. So for example, if we want the base color, then we set the value to 1 for the base color and 0 for all the others, and just to ensure that the function only bakes the base color to the render target. After setting the material parameters, we now draw material to a predefined render target and copy the results into a pre-existing texture map. And once all those texture parameters have been baked, we call a bit of Python at the end to set the texture compression and alpha settings correctly. We create a material instance of the UEFN parent material and then assign the baked textures as material instance texture properties or parameters. This script also copies some other parameters over, such as like fuzz for fabric, world position offset on the neck, and then that result is saved in a specific folder. So none of the final decisions were made for any of these areas until we could see the results on a target platform and really evaluate visual quality and performance. In our case, it came to looking at them in UEFN. So regardless of performance, we wanted to make sure that we maintained the high level of fidelity we've come to expect. And we did a lot of comparisons to determine what we could and what we couldn't reduce in order to keep that visual fidelity high. We also realized that having an accurate representation of all the components that make up your MetaHuman was really important to assess the actual size and performance statistics. And to facilitate testing grounds, we created smaller individual levels that maintain consistency with the main project to ensure accurate testing results. Creating these simple test levels allowed for an easier and quicker way to evaluate and test results and isolate problems without being bogged down in the main project. So I definitely recommend making smaller test levels. I did want to mention a really great overall profiling tool that actually I just learned about in UE. It's in the right-click menu, and it's called the size map. It's an interactive map showing the approximate size of an asset and everything it references. So this is a good way to see and verify how much will actually be loaded when an asset is used in a level. The assets are displayed and arranged from largest to smallest, and the tool allows you to zoom in and out to dig deeper into the dependencies of your asset. So I was kind of blown away by this. I've been working in UE a long time, and I had no idea it was there. So it's really cool feature. All right, so to illustrate a profiling example, this round of profiling we did looks at UEFN spec MetaHumans running in UE5 level on PlayStation 5. The environment's almost empty, and the lighting setup includes only a skylight and one shadow casting spotlight. And the aim here was just to simply find out how many MetaHumans we could get on a screen at various quality levels and target frame rates and resolution. So now these numbers are not guaranteed for you, but as there are many factors that kind of go into this, but this is just an internal example of something that we did to get performance information in this scenario. So please keep that in mind as we look at some of these. So this and the following slides are the results of the various scenarios we set up, and here we wanted to maintain a dynamic resolution of 1080p and then see the results of the GPU time in milliseconds. So in the top scenario, we tested 2 Lot 0 UEFN MetaHumans with fully simulated strand-based hair, Hudson being one of the more extreme examples with really big hair and beard, and that gave us a time of 7.1 on the GPU milliseconds. And the next scenario below it, we tested 3 Lot 1 UEFN MetaHumans with fully simulated strand-based hair, and this ended up being a little bit more performant at 5.1, simply because of the lower LOD and simpler grooms. We then switched over to use hair cards in this scenario, so 3 Lot 1 UEFN MetaHumans with fully simulated card-based hair, and we can see that this is more performant because of the card-based grooms. Pretty good jump there. And then we added 3 more MetaHumans with card-based at the same quality level for a total of 6 characters. There is a 1.3 millisecond jump, but we also have double the characters. And then we wanted to play with a more hero-type character with some background characters, so we added 1 of the Lot 0 with full simulation hair strands, and then 5 UEFN Lot 1 versions with hair cards for the background characters, and that put us at 6.1 milliseconds. And then to compare to that, we changed the hero character to use simulated hair cards, and the background characters, we switched over to use hair helmets, and you can see the bump in performance there in the card-based version at 4.7 milliseconds. For the last scenario, we just used 6 of the highest level possible with full strand hair-based simulation. This got a bit expensive at 11.3. And then by dropping those same 6 MetaHumans down to Lot 1 and using just the card-based strands, you can see the bump in performance there. So there's a 7.1 millisecond gain there. Basically, hair strands are expensive, is what it comes down to. So all of the optimizations that we were being made, big or small, contributed to the success of MetaHumans in UEFN. These improvements that we learned will also benefit the Unreal MetaHumans in general. You can expect some of these improvements to be rolled back into the Unreal counterparts, as well as having the option for the optimized MetaHumans as well. When all is said and done, we looked kind of back at the overall impact of each area, and here is a rough relative scale of how each area contributed to the overall reduction in size and performance. So texture optimizations had the biggest impact, while grooms came in next. And the one caveat to grooms, though, is that the chosen groom and the complexity of it really does have the overall biggest impact of size and performance. Animation improvements has the biggest range of optimizations, so depending on how you choose to leverage those, and reducing the total amount of LODs was an easy win to start us off on the right foot. All right, let's change gears a little bit now. I'd like to talk some about really cool, exciting updates to simulated clothing in Unreal 5.4. Clothing is an integral part of making characters truly believable and can be a visual expression of a character's personality. And creating clothing and getting them into your projects is not always an easy task. And in order to make this whole process a lot smoother and easier for you, we're excited to now have a pipeline that allows us to integrate clothing directly from outside software packages like Marvelous Designer and Clo. So clothing is very important to MetaHumans, and having more clothing assets in MetaHuman Creator is probably one of our most requested features. So during GDC, we announced that we teamed up with the digital clothing company Glow and bring in this pipeline not only to MetaHumans, but the Unreal Engine as well. And so now we'll look into more of how we use Marvelous Designer in the Talisman and show you details on how the new cloth pipeline works. The USD format allows for clothing panels and sim parameters to translate directly into the engine. And so this new process, which is available in beta and 5.4, allows you to easily see the real-time representation of your sim from Marvelous Designer or Clo really quickly. Alternatively, you can import traditionally authored static or skeletal meshes and set them to be simulated as well. And once they're in the engine, you have the option to use those results in Unreal, or you can export them to be used in UEFN as well, and you can expect a one-to-one result between UE and UEFN. So at Epic, we used Marvelous Designer to create the costume for Rue, which is our captain in Talisman. And here you can see we use one of our stock MetaHuman bodies from MetaHuman Creator to construct the costume. You can begin your creation process in Marvelous Designer, just like we did. And then when working in Marvelous, your fabric selections and simulation settings matter. If you choose to transfer these simulation process those simulation properties during the USD process, we take into account those attributes, and they will affect the simulation behavior in Unreal. Once you're finished, the new USD export is a really easy way to get your clothing assets out of Marvelous and right into the engine. I would like to emphasize that Marvelous Designer and other external packages are not needed to use the new cloth workflow. We simply just provide an easy way through the USD file import to get it from Marvelous and into the engine. So also having cloth panels is not a requirement either. If you import like a static or skeletal mesh, the UVs become the panels, and you can use any of the tools just like you would if you had panels. Obviously, you can use the clothing system for more than just clothes. Here I've just included a few examples of other cloth stuff like flags, banners, and then I used cloth for the tentacles and arm of the jellyfish. So it was really fun to kind of just do something not cloth or clothing. All right, once you've imported your clothing assets into Unreal, we can now start setting up the cloth panel graph, and you can choose a workflow that ranges anywhere from a fully automated to a completely hand-tweaked setup. This flexibility allows you to get something up and simulating faster, as well as having the option to completely customize any areas of that graph that you feel are necessary. At any point in time, the cloth asset can again be used in UE or migrated to be used in UEFN. And to get the clothing onto your character, you simply add a chaos cloth component in your character's blueprint, and then choose the corresponding cloth asset that you would want to use. So a new feature that we've added is an auto-generated graph that's built when you first open a cloth asset node, and this feature streamlines the cloth setup, allowing you to arrive at a simulation much quicker and faster. And more easily. This includes the USD import nodes, some core nodes for setting up the simulation, value transfers from Marvelous Designer if you selected it, a physics asset node, and parameters to set to good initial values. And one of the best features of the pipeline, though, is not only do we provide an automated path for you, you can also customize basically every part of that path to whatever suits your needs. So for Talisman, we decided we really kind of wanted the best of both worlds. On the automated side, we use the remesh node to auto-generate lower resolution meshes for the lower laws. But we also felt that there were assets that we wanted our artists to customize and tweak to fit our needs. And so, for example, we created our own custom high resolution render mesh for the captain's costume. We tuned skid and weighting for lot 0, and we dialed the simulation graph to meet the needs of our project. Another really cool customization tool or thing we use is the new kinematic collider, which you see over here. This is a deformable collidable mesh that moves with the skinned asset, and this allows for much more accurate collisions at a actually quite relatively inexpensive price. And the kinematic collider is easily set up in the graph, and it solves so many problems that come from just using capsules. And if you've ever used that, you know what I'm talking about. All right, so let's take a look at the cloth panel editor now. So the cloth panel editor was released in 5.4 and introduced a new way of authoring cloth. The panel editor is where all your clothing graph work will be done, and there's basically 4 main sections to the editor. In the top left is the panel viewer, where you can see 2D and 3D representations of your asset, make selections, paint weights, and maps. There's been a lot of tool improvements here made for easier painting and selection, and we'll continue to refine those tools and processes there. In the middle of the editor is the simulation viewer. Here you can view the actual simulation behavior, play animations, use different meshes to view your cloth on, and see all the visual debug tools. On the far right is the panel for simulation details, preview scene settings, and the simulation visualization tools. These preview settings, the preview setting tab allows you to set skeleton meshes and animations to view your clothing with. The details panel has a lot of the usual settings that pertain to the clothing asset. The visualization panel has a lot of great features, like seeing only the simulated mesh, which you see here, displaying collisions, viewing weight maps, simulation statistics, and others, just to name a few. Last but not least is the data flow graph there at the bottom. This is where you set up your graph and access the nodes to create different cloth features. It has a very similar feel to wiring nodes like blueprints, and once you're done setting up the graph in the panel editor, you're now ready to use that cloth asset in UE or again in UEFN. But let's now take a look at a couple nodes that could be of particular interest. So this new transfer skin weights node is a new tool that we've added, and this node allows you to take an imported static mesh or assets coming from the USD, import and copy weights from a user-defined skeletal mesh to the chosen mesh. Since the cloth solver needs to have weights in order to work correctly, this is a great solution that skips the need for you to rig and weight your clothing mesh in an external DCC. So in most cases, all you'll need is a rigged body, most likely your character that you're putting the cloth on, and then your static mesh as inputs. The output of this node will give you a skin version of the static mesh now ready to use in the clothing asset. So it's worth noting too that this algorithm that's used is different than what you would find in some DCC packages. It's called the in-paint weights method, and it allows us to significantly better handle loose clothing as well as armpits and other tight areas on the mesh. You can also use the skin transfer node if you don't want to simulate your clothing at all. You can just use this node in the graph without any other simulation nodes, and the end result would be a rigged version of your cloth moving with your character. And we actually use that technique for the LOD 2 of our Talisman character. So for lower LODs where you don't want to pay the expense of simulation, you would simply just kick out this rigged version, skin version of it. The remesh node allows for auto-generation and lower resolution meshes based on a target percentage. You can choose to remesh both the render and the simulation mesh, or just one or the other. For creating LODs in Talisman, we took the hybrid approach. We hand-created our render mesh LODs, but used the remesh node to auto-reduce the simulation meshes. Here you can see some of the numbers that we targeted for both the simulation and render mesh. In the end, we decided to keep the same render mesh for both LOD 0 and LOD 1, as we felt the lower resolution actually wrapped better to the simulation mesh. So depending on your project needs and complexity, these numbers will be different for you. So Roost Jacket is 100% simulating using self-collision and a kinematic collider, and real-time simulation is not an easy task. It's always a give and take relationship between performance and quality. Our goal is to make real-time simulation a lot more widely usable and performant-friendly. For Talisman, our target was about 30 frames a second on a high-end machine, going for high-end quality simulation in a close-up scenario. The lower LOD simulation frame rates came anywhere from about 50 to over 60 frames a second, 50 to 60 frames a second after tuning the graph for those specific LODs. Total simulated vertices, self-collisions, and solver iterations being the biggest factors for improved performance. This was the first project that we used panel cloth in a production environment, and we learned a lot. Here are a few things that I think are worth mentioning. If you're importing from Marvelous Designer, you have the option to use render mesh that comes from there. Unless you're just experimenting with cloths, you'll most likely want to create your own render mesh. You'll appreciate the greater mesh flow control and art direction. Higher vert count isn't always better. We originally had Lot 0 render mesh with about 90,000 verts, and we thought we could get a better looking sim with a higher vert count, but since the render mesh is essentially shrink wrapped to the sim mesh, there's a point where the higher vert count actually starts to reveal the shape of the underlying sim mesh, and so we ended up choosing lower vert count because it actually wrapped better and looked better than the higher resolution. Having good co-spatial relationship between the render and sim mesh is important. You want both meshes to match positionally quite close. We had cases where parts of the render mesh didn't line up very well with the sim mesh and caused weird spikes when simming, and the proxy deformer had a hard time figuring out how to wrap those two because they didn't line up very well. Also, make sure mesh pieces aren't modeled too close together. We had a scenario where the front part, the front belt strap was modeled really close to the panel of the front, and essentially got stuck to those two got stuck together because there just wasn't enough space for the wrap deformer to figure out how to do that. So just having a little bit of extra space there would have saved us a lot of time and hassle. I used 2 separate cloth assets for the Talisman demo. We wanted more fidelity in the helm sequence, so I tailored the settings heavily to look best there. In addition, I set up each lot to hit a specific performance target as for all the different consoles. So when trying to figure out the best setting and methods, I used the LOD path for not just lodding, but actually experimenting, which I actually found out to be really helpful. So instead of deleting or removing nodes, I could just branch off and create a new scenario, and just that would be that next LOD. And so I could flip between the different LODs and see different results without having to destroy or delete, remove nodes, unhook, stuff like that. The kinematic collider is awesome, and it's quite cheap computationally. Outside of simple collision needs, I'll likely use this going forward. And you can further optimize it as well through selection sets. You can reduce verts that it's actually colliding with, and you can also delete sections, so that will help with performance as well. Just solver settings make a big difference, obviously, with iterations, and in real-time scenarios, those will most likely be lower because you need the performance. And there's a node called the long-range node, which essentially helps reduce the stretching at lower iterations, and that was a big help. And finally, there's lots of things we want to improve, so if you use the tool and run into issues or frustrations, please let us know. It's a really big help and actually helps us prioritize things that we work on. All right, really quick, looking at the time. So just once you've created your cloth, just a really quick way to add custom clothing to your MetaHuman. In the main MetaHuman blueprint, you see all the components that make up the character, and if you have a skin piece of clothing, say like a tighter fitting shirt, you can simply select find the corresponding skin mesh, and then just swap out that mesh, and then that asset will show up there. If you have a simulated piece of clothing, like in this case, you add a chaos cloth component to the blueprint, parent it under the appropriate component, most likely the body, and then choose the cloth asset you set to use, and you should be good to go. For example, in this picture, I've combined the shirt and pants into one skeleton mesh and replaced the body mesh in the body component. And then I also swapped out the original shoes to use the space, and then I've left the face component and all the groom components alone. I've removed the unused components from the setup, and then to use the simulated jacket, I added a chaos cloth component and paired it under the body. Just when making custom clothing, just make sure you're aware of the body type that you're using, otherwise you could probably clip. All right. We've covered a ton of information today, so let's just touch on some of the highlights. When creating performant MetaHumans, we looked at 4 areas of the the number of nodes used, animation performance, groom optimizations, as well as material and texture savings. Use the profiling tools to help you better understand what's expensive and where to start optimizing. And then you can import your clothing from software packages like Clo and Marvelous. You can utilize both automated and custom setups, set a cloth asset graph, and use those both in UE or Unreal. All right, with that in mind, I'd just like to say thank you for joining me today. I hope you found something useful, and again, thank you very much. Thank you, not only you guys, but also the amazing team that I worked with. So, thank you very much.